Let's think about an experience that just about every single one of us has had at some time in our life. You are standing comfortably in a bus at rest, and all of a sudden, the driver starts the bus. What happens? Yes, you get thrown backwards with a jerk. But why does this happen? Before answering this question, let's think about what was done so far in the field of physics at the time of Galileo and Newton. Before these two, it was believed that any object will move only if a force acts continuously on it. It was Galileo and Newton who showed that this was not the case. And we will understand why earlier scientists like Aristotle and Socrates made this mistake. The very first law that we will encounter is the law of inertia. The law of inertia states that an object will continue to be either in a state of motion or in a state of rest unless compelled by an external force. A common example of this is the bowling ball. We know that a bowling ball requires a lot of external force in order to get going. We also know that a bowling ball is very difficult to stop once it gets going. This means that nature has no real preference for either state, neither stillness nor motion. Either state will continue indefinitely if no force is acting on it. So let us understand that why people before Galileo and Newton made this mistake. So what was the reason that early scientists made this critical error? The reason was the absence of the idea of friction. Friction is a force that opposes all motion. So because we did not understand friction, we came to the erroneous conclusion that an object will only move continuously if a constant force is applied on it. So the law of inertia, which was formulated by Galileo, was then rephrased in a slightly better way by Sir Isaac Newton. What did he say? He called it the first law of motion. And he said that an object continues to be in a state of rest or of uniform motion in a straight line unless compelled by an external force. This is the first law of motion. Now, both the state of rest and of uniform motion or unchanging velocity implies zero acceleration. This means that any unbalanced force on an object will result in the acceleration of that object. In other words, we can say mathematically that the acceleration of the object is the mathematical ratio of the unbalanced force acting on the object divided by the object's mass, or in other words, the object's inertia. Or we can say that force is the product of mass and acceleration. Thus, acceleration A is equal to force divided by mass, or conversely, force is equal to mass m multiplied by acceleration A. Thus, if acceleration is 0, the effective force acting on the object is also 0. Coming back to the example of you falling down in the bus, what exactly is happening here? When the bus starts moving, you, being already stationary with respect to the bus, want to remain in that state due to your inertia. So it is not really a case of you falling back. It is a case of the bus moving and you remaining exactly where you are. And now we come to the second law of motion. Have you ever observed how a seasoned cricketer will draw in his hands during a catch? They don't just catch the ball, they are moving the hands along with the ball in the same direction. Why is this so? The answer lies in the second law of motion. Before we understand the second law in detail, let's introduce a term called momentum. Simply, momentum is defined as the product of mass and velocity. Mathematically, P, that is momentum, is equal to mass m multiplied by v, the velocity of the body. Thus, P or momentum is the product of mass and velocity of a body. It is the characteristic property of any moving object. Now, let's clarify this concept called momentum just a little more through a few questions. Number one, which one would require more force to move? A car or a truck? Also, which one would pierce into your body tissue? A bullet thrown at you or a bullet fired from a gun? Yes, the bullet fired from a gun will pierce your skin. Similarly, a truck is much harder to start and to stop compared to a car. You need much greater force. And the reason is that the momenta of these two systems are very, very different. In the case of a car and a lorry, the same force applied at the same time on both bodies will produce very different accelerations because the car is much lighter compared to the truck. But the change in momentum will be the same for both of them because even though the car is lighter than the car is also moving much faster than the truck. The lower velocity gained corresponds to the greater mass of the object and vice versa. And this brings us to Newton's second law of motion. The same force at the same time is causing different changes in momenta. So how do we put this into a law? The second law of motion by Newton states that the rate of change of momentum of a body is directly proportional to the applied force and takes place in the same direction in which the force is acting. So mathematically, if dp is a small change in momentum and dt is a small change in time, since p is equal to m times v and mass remains constant, we can say that the change in momentum can also be defined as the rate of change of the velocity multiplied by the mass of the object. In other words, we can say that the rate of change of momentum is equal to m times dv by dt. In other words, we are redefining the first law in terms of momentum. That is, force is mass multiplied by acceleration. Coming back to the question, why do fielders draw their hands in the same direction as the ball? Well, the faster we slow the ball down, the greater the force required and the greater the force exerted on our hands. If we try to catch a ball quickly, the ball has to slow down very quickly, which means its momentum changes very quickly, which means a larger force is exerted on the ball and on our hands. To avoid injury, the cricketer will draw his hands in the same direction as the ball's motion to slow down the ball a little slower, thus reducing the change of momentum, thus reducing the effective force on his hands and on the ball. But this brings another question. What happens if you try to catch the ball very quickly? There is one more term we have to familiarize ourselves with, and that is impulsive force. An impulsive force is a large force acting in a short period of time, producing a finite change in momentum. When you throw a ball at a wall, it rebounds very quickly. So, the velocity of the ball is changing in a very short time. The momentum of the ball is changing in a very short time, which means a large force is being exerted by the ball on the ball for a short amount of time. And this kind of force is what we call an impulsive force. Impulse can be defined as the large force multiplied by the time, and that is equal to a change in momentum. And this brings us to the third law of motion. Have you ever asked why helicopters stay up in the air? What are they doing to stay up in the air? Why does a book rest on a table and not fall through the table towards the earth due to gravity? Well, the table is exerting a force on the book and the book is exerting a force on the table. In the same way, the helicopter is exerting a force with air towards the ground, and in return, the air being thrown down is exerting an upward force on the helicopter. And all of this is because of Newton's third law. Newton's third law states that every action has an equal and opposite reaction. In other words, it is impossible for a force to act in isolation. Forces will always act in pairs, and these pairs will be equal in magnitude and opposite in direction. Mathematically, we can say that the force exerted by an object A on B is equal to the negative of the force exerted by the object B on A. So these action-reaction pairs exist in any case where Newtonian forces are being exerted. No force can act in isolation. Action and reaction occur, for example, in this case. Hot gases are being ejected downwards by the rocket. So the rocket is exerting a force on those gases. And conversely, the hot gases are also exerting a force upwards on the rocket. Thus, we are seeing a system in which there are two forces acting in equal and opposite directions. Now, there is a misconception that we have to clear about Newton's third law. Children often ask the question that if the forces are being exerted in equal and opposite directions, then wouldn't they simply cancel out? In that case, the net force should be zero and nothing should be happening. For example, if we look at this equation, it says FAB is equal to the negative of FBA. But notice what is happening here. One is the force exerted on A by B, and the other is the force exerted by B on A. This means that Newtonian forces, the reaction forces and the action forces are not happening on the same object. They are not exerted on the same object. So always remember, action and reaction do not take place on the same object. The only way the sum of these forces can be zero is if the forces are acting on the same object at the same time, which is clearly not the case here. Now let's summarize what we have learned so far.
Manorama Horizon. Learning made simple.